Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture video 9, and we are in chapter 3, OneWay ANOVA. And today, or in this video, we are going to go through the code. So as always, we're going to use RStudio, and we're going to, I've provided this file so you can work through this with me. I'm not making you type in the commands or anything, but you will have to know how to use this in order to do some homework and, more importantly, how to do the projects. And the projects, just to remind you, have to be professional. This course is to prepare you, to help prepare you to be a statistician. And when you graduate with this course, as a senior, you should be able to go out into the workforce and perform as a statistician and do applied analyses and be able to report it professionally. And by doing this, you will make yourself look good, and this will give you job satisfaction, I would say, because your boss will be happy, other management folks in your company will be happy, and they will know that you know what you're doing. All right, so that's why I'm stressing the format so much. So again, this is our Stat 400. This is the Chapter 3 code, and we're not going to go over the whole chapter. We're just going to do part of it. Now, this is an RMD, or R Markdown file. Okay, and for those of you who haven't used that before, done, we will come up here to knit, and we will knit this to a PDF. You can use HTML, you can use Word, or PDF. I prefer PDF only because that's how I'm going to grade it, is using an editor that can edit PDF, but not anything else like Word or HTML. Okay, so this is called our front matter here. So when you do your assignments, please make sure to change the name to you and change the date, and in the title put the homework or the project, whatever it is, up there, please. So change that. I have put some special chunk options here because I want to use something called cable, which is an HTML output, but I want to be able to use it in PDF, and in order to do that, we need this special code here. And so this is a little bit of an introduction about this chapter. It won't be in the file that you received. This will not be there because this is for my lecture, not for your work. Okay, so you would change all of this and put in your problem, and that's all you would really need. You don't even have to put anything right here because it's before the first chunk, and you will see where we have the description of the problem a little bit later. So we have our global settings. Now in each of these chunks, which are in gray, we have some options. The first option here, well, we have some modify chunk options, so I don't really use that. I will come up here, and this first thing says use R instead of Python or anything else that RStudio uses. This is the name of the chunk, which is optional, but if you use it, then each one has to be unique, or else it will not compile or knit at the end. And then if you want some other options here, you can put a comma. And for some reason it's not doing it now, but earlier today when I did a comma, it would do a drop-down box of the different options. But up here under help, there are cheat sheets. And so R Markdown cheat sheet and the R Markdown reference guide are good guides to tell you how to modify your settings on these chunks. So that tells you whether or not you're going to include the chunk, whether you include the output from the chunk in the document or not. And so these are important settings. We're using knitter, which is the package, and then we've got the chunk options set right? So we're setting these generic options, but we can override them in each of the individual chunks. But I'm saying, do not tell me about warnings. Well, if you're getting an error, you may want to change this to true, or you may want to change it to true in a certain chunk. The other thing is I don't want to see messages, because sometimes that really clutters up my document and I just don't want to see all these messages that I don't need. Echo equals true means to print this code in the final document, which I want you to do. I want to see your writing, your output, and your code, both. And then figure a line, putting it in the center. That's just kind of a standard thing we do. That's what most professional software packages do for us. And then here, sometimes I want to debug something, and to do so I need to see all the output, or I want to see a very large item, maybe a really long matrix or a really long vector, and it stops at a certain number of lines. So I've put in a huge number of lines so that I don't have that issue. And then this is to turn off scientific notation unless it is more than 6 decimal places before your first, or 6 zeros before your first numbers. So after that, I'm okay with it. But if it's 4 or 5 decimal places, I want to see it printed out. If you want to turn it off completely, which can make a mess, you can change this to 999. And that is actually what I'm publishing to you as the student, is with it completely off. But you can change this value, like I said, to like a 6. Okay. So we've already talked about the name of the chunk, so I don't need that in there. And so here we have R, I'm calling this packages, and then I don't want this in my document. So I'm saying include equals false. Don't include this in my final professional document. Nobody really cares too much about what packages are in there except you. And so I've put in all the packages that we need. Now, if you don't have one of these packages installed, then usually up here at the top, there will be a little thing that says you require these packages, install now, and you can click on them and install them. Or if you don't get that error, but when you go to, say, the library, load it, and it says it's not there, that there is no tibble, let's say, then you would come up and you can uncomment this. The way you uncomment one line is to hit Control or Command if you're in iOS, Control, Shift, and C. And then that uncomments it, and you can run this. And of course, if you have to install more than the one, you can copy and paste and change the names, etc. Okay? So, actually, so we're going to run that. So I was telling you, here's the settings. Here's an option to run all chunks above it. It does not run this chunk. It will run all the chunks above it. Right now, there's only one above it. And this has the option too, but there's really nothing above it, so that doesn't make much sense. But this arrow to the right says run the current chunk. So I'll run it, sets my settings. And then here are my libraries. And then here is another statement that has to be in there in order for us to be able to use the HTML output, that cable, which is really nice and professional looking. So I found this on the internet in some forum as an answer for somebody who was trying to do the same thing, and so I've used that solution here. So we'll run this chunk. Now I don't have to run these chunks one at a time, but I often do the first time. I can come up here on the top right of this console of the code window, and I can say run, and I can choose any of these if that's what you prefer. You could run all. I rarely do run all until I've debugged the code, because otherwise you're spending a lot of time for it to maybe crash and you try to figure out what's going on. And you may not be ready to run it all. Okay, so I've run this chunk, and now we have the example. I'm not going to read through it because we've had that in the notes, but it is in the file. And it's talking about the problem. And I do want to say that This is math mode. These dollar signs, you'll see now that my mouse is over it, says n sub I equals 5. So you do an underscore to do a subscript, and you do a caret to do a square. And you can do both. And so I've given you these examples of what to do. And I've got some other information in there where we're talking about an efficient way to generate the random order in Excel is to use the rand function, okay? But we're not going to use Excel in this portion, so we don't need that. And so instead we could use this code to randomize them if we were setting up the problem. So since we're not the people designing this experiment, and here's an example of the order that it would come in, then we're going to get rid of this. So this is going to go away. All right. Now, these V spaces are vertical spaces, and they allow you to control the spacing because R wraps things that you don't want to wrap. And so you'll see at some of the sentences at the end, in order for the next sentence not to be a follow-on or wrapped up with it, it doesn't matter if you put spaces in between it and then type. It's going to take this when it prints out and it's going to put it right there. And that's not what you want. So one of the ways to say make a new line is to go space, space at the end of your sentence. And then if you want a blank line, space, space, and then you can type, and there should be a space in between it. Another way to do that is with this VSpace command, and that allows you to specifically set how far the distance is. Okay? And so I think we have to have it right after the sentence for it to work. Now this is my data, and I've provided you Excel spreadsheets so that you can copy and paste the data for the problems right over here. Now be careful. This is a publisher's spreadsheet, and I've found a lot of mistakes. And you have the book, so you need to check to make sure that the data that's saying it's problem 10 is really for problem 10 and not 11 or 9, where the publisher changed the version and changed the problem numbers and didn't update the spreadsheet. Okay? You're still responsible for using the correct data. So read the problem, look at the data in the book, and make sure that you find the right data. And if it's not in the spreadsheet, then yes, you would have to type it in yourself. All of the data will be typed in to this so that I can run your code without any issues. Yes, in other classes we've talked about how to import the data and to call it from using read.csv or read.table. Do not do that in this course. I will take off points because if I can't run your code, then you get a 0 until I can run your code. So, and that's a hassle for both you and I, and we don't need that hassle. So go ahead and put your data in here and line it up nicely. So when you paste it in here, it's probably going to look something like this. Actually, there. And there won't be any commas. So you'll have to put the commas in between the numbers. Now, remember not to put a comma after the last row, on the last row before the parenthesis, because otherwise if you put a comma here, it thinks that there's another data value, and you'll eventually see somewhere an X, a red X will show up. Okay, my computer's tired from being overused today, so it's not showing the normal. It's not acting normally right now. Okay, so make sure that you line up your work, and so it looks nice, so we can see what the number. This helps you as well, so that you can look down through here and you can see the values and read it easier too. Then we have by row equals true, yes, and then you'll have to change this to the number of columns. All right. Then you'll need to change the column names here, and there needs to be the same number of column names as there are columns here, and the columns here need to be the same number of columns you have up here. Okay. And then we make that a data frame, and here we're using the cable function to print. So I'm going to run this chunk, and here is my table with nice delineation between the rows. It's nice professional looking, and so you'll have to change your caption here. Okay, so you'll have to change your caption when you change the data to a different data set. So make sure that you change these things and modify. All right, so let's go ahead and get started. Descriptive statistics, I've written in here the type of analysis that I would do for this problem. So here's the descriptive statistics. I've used favstats, but you could use describe by. I've put in the cable statement for describe by as well. You could run that if you want, but I've chose to run favstats because I don't need the other things that are there, and I like the simplicity of this table. But again, that's a personal preference. You decide. And so when we run these descriptive statistics, we don't just say, here it is. We look at them and we see, what is it telling us? So one of the first things we look at are the means. And as the power increases, we see that the mean etch rate increases. Well, what about the median? We see the same thing there. What about the min? We see the same thing. Q1, we see the same thing. Q3, we see the same thing. The max, we see the same thing. So that's the important, what is happening in our data as our variables change. How can we look at this and what does the data tell us? And then remember that for ANOVA, we're supposed to have equal variances between all of these. And I see that 160 and 200 are very close, and then 180 and 220 are fairly close. But is, the 15 to 20 something, is that really close enough to be from the same, having the same variance? We'll have to see when we test it. So I've put in the analysis here. Please look through it. Oh, by the way, this \approx is how you get the squiggly lines there to say approximately. Okay. And if you have questions about what I'm typing in and why, as far as those math codes, please let me know. I'm happy to help you. So that's our descriptive statistics. The next thing we want to do is graphical analysis. I think there can't be a space in between this pound sign and the descriptive statistics in order to make it a hyperlink in the document. And so we're going to first look at histograms. But remember, we only have 5 observations for each power level, and we have to do a histogram for every treatment because remember, those are individual populations. So when I run this, and I've put them all on one graph, I don't get very much. Okay? It doesn't tell me anything because there's only 5 observations. I can't see if this is normally distributed or not. There's no way to tell. So I would not put in the histogram in this problem. I'd wait until I had maybe 15 or 20 observations in each treatment level before I did the histogram. So I would simply delete this from this file. In fact, well, no. Okay. So I would completely get rid of histograms here and remove this. But I've put this in there in case you want to use this for another assignment or a homework or a project where you do have the right number of observations. You can look at the histogram. So you can look through here and see the code. I've put some comments to explain what we're doing. And again, if you have questions, come to office hours. I'm happy to walk you through this. Okay. And then we've got dot plots, and you've seen that in the lecture notes. I showed some dot plots, I think in chapter 2. And we can see again that we have, as the power increases, the etch rate increases. It seems to, in general. And so that's what I've said here. The next graphical analysis are box plots. And so I've given you the code there, and we're putting all the box plots on one plot so we can compare them. And we see when we're talking about box plots, the bold line in the middle is the median. That's what we have to talk about. We don't talk about the means with box plots because the means aren't anywhere on here, but the medians are. We can also tell that these boxes, this box here for 160 is skewed to the right, because if I rotated this clockwise, the box on the right would be bigger than the box on the left by a lot. And then 180, 200, and 220 are skewed to the left. Okay? And I've put that in my analysis here. So you need to look at these graphs and say, what does it tell me? Don't just say, oh, here's the plot. You have to look at it and say, what is this telling us about it? Does this give me some information before I run the experiment or before I run the analysis? And then next are QQ plots or quantile plots. We use this to check for normality. And this is basically the best method to use, especially with small sample sizes, because you'll see I've put the code in here for formal normality tests, but the thing is that they are often wrong simply because they're very sensitive tests. And so if you have an outlier, just one outlier, then usually the test fails. You can't say that they're equal, or you can't say that they're normal. The distributions are normal. So this QQ plot has a lot more leniency, if you will. In other words, it's open to interpretation better, and we can usually interpret the plots better than we can run this unforgiving test. Okay? So the code's in here. Again, I've changed my Y limits and my X limits. So as you change the, and then you would have to change the caption. So there's things that you have to change when you change to a different problem. Okay, and so I've done this for each of the power levels, and I've made it so that it's on one plot so we can compare them all at one time. Now I've got two different QQ plots in here. This is the first one. You would never put both of them in here. You would only put one of them. Okay, so you have to choose which one you want. When I look at this, the only concern I have is right here on the QQ plot for power equals 160, near the middle of the, in fact, it is the middle point. It's a little ways away from the line. We're not so concerned when in the tails, as I mentioned in chapter 2. If you've got a point that's out here that's an outlier near the tail, you can kind of expect that. That's okay. It's in the center of the line that we want to see a very good fit to the line. So with this being a little further away, it makes me question, is that a problem or is it okay? Okay. And so, so again, I've put my analysis here. We do not see evidence that the normality assumption has been violated, but I do have a question. So instead of using this QQ plot, I would use the next one. I would run this and then I would remove it from my code. Again, I'm leaving you all of these options so that you can choose which ones you need in the homework. So because one of the points at the power level, 160, as I said, deviates from the QQ line near the middle region, we're going to run this next one, and the difference is this is QQ plot with a capital P. This is QQ norm, and then I have to call a QQ line separately. But this does it all together. QQ plot is a more sophisticated function that someone programmed, and so it puts everything together very nicely. I can change my Y limits, but I cannot change my X limits. That's the downfall. And it goes ahead and puts the 95% confidence bands on the graph. So let's take a look at that. And here it is. So those dotted lines are the 95% confidence bands. And you can see that this point is well within the confidence band. It does not exceed it. And so none of the points in any of the graphs go beyond the confidence band. So we're now very comfortable saying that these are that we can assume that these are normally distributed, or what we say is we don't see evidence of any violation. So to verify, this confirms that there are no evident violations of the normality assumptions for any of the power levels. So you have to give the analysis, all right? And then we have these normality tests, okay? And so you could run this. I've left this in here, but I would not include it most of the time. But here they are. And what you're looking for is you're looking for a p-value that's large. because the null hypothesis is that it's normal. The alternative hypothesis is that it's not normal. So you want the null hypothesis to be true. When I see a 0.27 for a p-value, it makes me a little nervous because it's pretty small. Then I see a 0.97 and I say the largest it can be is 1. And so this means that the probability that so the probability that I would reject this and be wrong if I rejected this is 97%. So if I say that they're not equal, the probability that that I'm incorrect is 97.3%. That's huge. That's great. That makes me feel good that these are actually normally distributed. And here's a 0.87. That's great. And here's a 0.94. That's great. So and this is the Shapiro-Wilk normality test. So the only one that I have questions about is the first one. And if you remember the QQ plot, it's the one with a point in the middle that's further away from the line. So this makes sense that it's just an outlier, or not an outlier, it's just a more extreme point that's lowering the p-value. But when we look at this, we do see that it doesn't have a different shape than the line. It's not like it's going off in a curve away from the line, or it's a parabola or something. These points do follow the line, which indicates that it is normally distributed. Okay. So we've got the official, and then these are very, very sensitive to outliers. So you can see just that one point that's not very close to the line, drop this to a 0.27, 0.28 compared to the others. Okay, and then we've got the chi-squared test, and so it's a test for normality as well. We can see those p-values. It's not as concerned about that first, the power index of 160. The others are 0.75, 0.61, and 0.86. Okay, so these all test a little differently. Now, in order to do ANOVA, we need to test for the equality of variances. So we need to check the assumption. And what we usually, the test we like to use is Levine's test because it's less sensitive to the outliers or departures from normality. Okay, so if you have an outlier and you use the F test, you might come back and question whether or not your variances are equal, and it may be because of that outlier. Okay, and so you can see that we're using an F test, and here's my null hypothesis. Here is my alternative hypothesis. Okay, so we've got the alternative hypothesis, and then I not equal to j, and we have multiple of these. We have 4 different variances, and we want to know that they're all equal. So we run this code here, and we're able to do it on all. We have to make power a factor, or else it doesn't work in this test. This test will return errors. It may not tell you that it's an error, but it's going to return junk, or it just won't return anything and will tell you it's an error. I don't remember which it is. So again, we're following the same pattern. We have alphas here. You don't have to say the model in this case. You're just saying the variances. And then you say the test statistic is, and we look down here, and here's an F. So this is basically an ANOVA table, except there's nothing on the second line except the degrees of freedom. So we have 3 degrees of freedom in the numerator, 16 in the denominator. Our F value is 0.1959, and then we have a p-value of 0.8977. So that's very good that the higher this number is, the more comfortable we are saying that those variances are equal. Because remember, we're using this test backwards from what it was intended. It was intended to test the claim, not the null. So just because you don't have, if you have a 0.06 here for a p-value, I'd be very concerned unless the test is robust against departures from equal variances, okay? But when you get these low p-values, even though it's not below 0.05, if it's below 0.1, you might be concerned that they're really not equal, okay? Because then there's the chance of you saying that they're not, when they are the same, is only less than 0.1, so less than 10%. Okay, so again, I've given you how I how I would analyze this. I say the test statistic is 0.1959 with, there's the degrees of freedom, which corresponds to a p-value. In this case, it's not small, it's large, so we put the value. We fail to reject the null hypothesis and conclude there does not exist sufficient evidence to support the claim that the variances for the different levels of power are different at a 95% confidence level. Oops, need to capitalize that. The test was performed using N1 equals N2 equals ... N4 equals N, which is 5, observations per treatment level. Okay, so this tells you exactly how many observations were done and gives the reader a very clear picture that all the sample sizes are the same and that they're 5. Okay. Then we're ready to perform the OneWay ANOVA. So in this case, we have the AOV function, and I'm calling it ANOVA 1. This makes the code much easier because if you just run this, let's see what we get. We don't get what we really want from this. It just spits out some power, the residual, sum of squares, degrees of freedom. It doesn't do any of the calculations, the residual standard error, and it gives you this weird, if x may be unbalanced. What? Okay. So, but if I create this as ANOVA 1, then I run summary of it, I get the ANOVA table. And here is power. And here, remember, we got in the text, we got 66.8, and they get 66.8 in the computer. Now look at the p-value. 1, 2, 3, 4, 5, 6, 7, 8 zeros. So this would be 2.88 times 10 to the negative 9th. That's why I turned off the scientific notation, so that instead of getting scientific notation, I actually get the number. I can see just how small this is, this p-value. And then we've got the residuals. What we don't have is the total, but we really don't have to have the total for what we're doing here. And then these asterisks, you'll see that 3 is less than 0.01. Again, it's not 0. It's just saying it's closer to 0 than 0.001. But so whoever programmed this really should have done something a little different. And if there's 2 asterisks, it's less than 0.001. If there's 1 asterisk, it's less than 0.01. If it's a dot or a period, it's less than 0.5. And otherwise, it's between, let's see, so yeah, if there's nothing, then it's between 0.1 and 1. Okay, so. Oh, I see what this is. I'm sorry, I misread this. 0 means that it's, so the 3 stars means that it's between 0 and 0.001. Actually, this person did great with this, so I want to say, so 3 asterisks means the p-value is between 0 and 0.001, so it's significant at a 0.001 level. 2 asterisks means it's between 0.001 and 0.01, so it's significant at a 0.01 level. 1 asterisk, 0.05, a period, 0.1, and empty, it's really not significant. It's between 0.1 and 1. All right. And we've got the 3 asterisks indicating that it's less than 0.001. So then we say that the regression model for the experiment is here. Okay, so I'm sorry. So let's come back up to the analysis. So we've run this. Here's our ANOVA table. Here's what we put. We test for the quality of means for each level of power using the hypothesis, and here's our hypothesis. And since there's only 4, I can write all 4 of them out. If there were 10, I would not. I'd write mu1 equals mu2 equals ... equals mu 10. I would not write them all out. And the same thing for the alternative. Mu I is not equal to mu j for some I not equal to j at alpha equals 0.05, and that's our default. And then here's our model. Yij equals mu I plus epsilon ij. Again, put the I values of I, the values of j. The test statistic value 66.8 with 3 and 16 degrees of freedom, which corresponds to a p-value that's less than 0.0001. Okay, so when it's really small, that's how we write it. We don't put this number there. Okay, do not put that number there. That's not professional. That makes it sound like you're really confident that this number is exact, and we're not. When it's that small, we're certainly not going to say, well, it's precisely that. That's a really, really small number. So, we don't have that type of precision, okay, in our estimates. We just can safely say that the p-value is less than 1 in 10,000, okay? So because it's less than alpha, we reject the null. Hence, there does exist sufficient evidence to support the claim that the mean etch rate is different for at least 2 levels of the power using a 95% confidence level. You could say at least one level different. At least one level is different if you want. That's another way to say it. The test was performed using a sample of n equals 5 observations for each of the 4 power levels, and the order of the observations was randomized. Because in an ANOVA, that's also important that the order was randomized, and this experiment it was, of course. Okay, so that's as far as we're going to go because we haven't covered the regression model here. And so we will stop this video and this lecture here, and we will pick up after we discuss more information in Chapter 3. We'll come back to this file. Thank you for your attention. I hope this has been helpful for you. As always, if you have questions, come to virtual office hours. If you need help urgently or before office hours, email me. I will get back to you as soon as it's possible for me to. And please take care of yourself and stay safe because we really want to see you here next time.